All right, so welcome everyone to our last session in this course of Advanced Compiler Techniques, where we're going to talk about modules 186 to 190, which is about verification. So over to you, Arpit.
Yeah, thanks. Okay, so here's what we'll do. We'll first see a bit of a recap, then we'll move on to the part of the whole logic that's left, and then we'll move on to predicate transformers. So for the recap, we saw rules of Hoare logic. So I've just written them here. So the assignment rule says that if the predicate P with X replaced by E holds, then after assigning E to X, the predicate P holds. Then we have the composition rule, which says that if the triple PC1R holds and RC2Q holds, then the triple PC1 sequence with C2Q holds. Then we have the if then else rule, which says that if the triple P and B C1Q holds and P and not B C2Q holds, then the triple P with if B then C1 else C2 then Q holds. Then we have the consequence rule, which says that if P implies P prime, the triple P prime CQ prime holds and Q prime implies Q, then the triple PCQ holds. So this week we are looking at the Hoare logic rule for while. So the rule is that if the triple P and B CP holds, then the triple P while B and inside the while the statement is C holds, then the post condition P and not B holds. So here P is basically a loop invariant because P and so because it is staying invariant across each iteration of the statement. So we're looking at an example. So basically the precondition is x not equal to 0, and while x is greater than equal to 0, and while x is not equal to 0, we are decrementing x by 1, and the post condition we have to show is that x equals 0. So we can do a pattern matching similar to what we had here and take this as P. This the post condition as Q and this as B. So from the inference rule, we'll have that. So this is P and B, which we can show that so we can show that this triple holds P and B, C and P. We can also show that the P and not B, which is x greater than equal to 0, and x equal to 0 implies Q, which is x equal to 0. So then we have another example, which is this. So if sum is equal to 0 initially and n equal to n naught, which is both greater than equal to 0, and then while n is not equal to 0, it is adding n to sum and decrementing n by 1. So at the end we have to show that sum is n naught into n naught plus 1 by 2. So if we try to do the pattern matching here, so we'll have this the precondition as P, the post condition this as Q. So if we do P and not B, so that becomes sum equals 0, and so basically I've just written this and this. So we can observe that Q prime implies this Q, which is sum equal to n naught plus 1 by 2. This is because basically n naught and n and sum are all 0, which satisfies this equation. So we can try to prove this with the post condition Q prime, which is basically equivalent to saying sum equal to 0 and n is 0 and n naught is also 0. So which we can show that this is not a loop invariant, and this we can show formally. So we need to find basically a P prime such that across this body of the loop, this satisfies that P prime and B holds initially and P prime holds finally, and the precondition implies P prime, and P prime and not B implies Q, which is the post condition. So we can show that the that P prime, which is sum equals to n naught minus n into n naught plus n plus 1 whole divided by 2 works. So now the question boils down how we find this required P prime or the Q prime. So first we are defining these two things. So what is soundness? So soundness would be is that no erroneous fact can be derived by Hoare logic, and completeness means that all true facts can be derived by Hoare logic. But unfortunately, according to the Gödel incompleteness theorem, if the first order logic includes arithmetic, then there exists no complete axiomatization of implication in the consequence rule. In simpler words, we are saying that it is not always possible to find the required p prime, so Hoare logic is incomplete. But we have some good news in that it is relatively complete, meaning that all true facts can be derived by Hoare logic, provided the first order assertion language is rich enough to express loop invariants, and all first order theorems needed in the consequence rules are given by the programmer or by the oracle or something. So now we are moving on to predicate transformers. So why do we need this? So first we'll look at that. So Hoare logic we have presented a deductive system. We don't have any strategy to build the deductions yet. So weakest preconditions and strongest postconditions are complete strategies to build valid Hoare logic deductions, and they are complete assuming that loop invariants are provided by the programmer. So we're looking at weakest preconditions. For a statement S and a postcondition R, a weakest precondition is a predicate Q such that for any precondition P, the whole triple PSR holds if and only if P implies Q. So this weakest precondition is unique that if both Q and Q prime are weakest preconditions, then by definition QSR holds because weakest precondition is a precondition. And since Q prime is a weakest precondition, then Q prime implies Q, and similarly we'll get Q implies Q prime. And then from this we'll get that Q is equal to Q prime, or basically they are equivalent. So for the rules, we'll use the notation WP S, R, which denotes the weakest precondition for statement S and a postcondition R. So the first rule we have is that WP skip, R is R. So skip is a no-op, so the weakest precondition across a no-op is the same as the postcondition. Then we look at the assignment. So if X is assigned E and the postcondition is R, the weakest precondition is MS R, where X is replaced by E everywhere in the R. As an example, let's see the assignment being x colon equals x minus 5, and the postcondition is x is greater than 10. So just applying the rule, we'll have x greater than 10, where x is replaced by x minus 5, which we have x minus 5 greater than 10, which we can simplify to x greater than 15. So now we look at the sequence rule, which says that the weakest precondition of the statement S1 are followed by S2. Sorry, there should be a bracket here. The postcondition is R is equal to the weakest precondition of S2R, and then from that as the postcondition we'll find the weakest precondition over S1. So the example is that we'll see the combination of this x colon equals x minus 5 and x colon equals x minus 2, and the postcondition being x greater than 20. So we'll first so basically we'll first use the sequence rule to expand this. So this is just this rule that has been applied here, and then we have used the assignment rule for deriving this. This is x into 2 is greater than 20. Then we'll again use the assignment rule to derive this, and then which we'll get is the equivalent x greater than 15, which is the weakest precondition. Then we have the conditional rule, which says that the weakest precondition over the statement if E, then S1 else S2, and the postcondition R is equals to then E implies WP S1R and not E implies WP S2R. So basically we are taking just the preconditions over S1 and S2 and just combining them using this using the condition E. So let's look at an example. So the weakest precondition of if x less than y, then x colon equals y, else skip. For the post condition x is greater than equal to y. So we basically just first apply this conditional rule with from which we'll get this, and then we will just apply the rule for skip. Then we'll apply this rule for conditional, and Then we're going to simplify this equation. So saying that this x greater than equal to y implies x greater than equal to y is a tautology, and similarly y greater than equal to y is also always true. So we're replacing this by true. So implication with RHS as true is also true. So basically this says that the weakest precondition is true, which means that the statement is always true. So what are the semantics for our precondition? So, so if we have a statement S with a postcondition R, we want to find predicate just prior to the execution of S such that, so we have two options here. One option is if S terminates, then R holds. So terminates means that it completes execution and control reaches the PC just after S. And option two is that S terminates and R holds. So option one, we are writing it as with this curly braces, and this is the whole triple for partial correctness. And option two, we are writing with this square braces, and this is the whole triple for total correctness. So the precondition will get with this these semantics, which will be called the weakest liberal precondition, and with the total correctness semantics, we'll get the weakest precondition. So we can observe that WP implies WLP, because if S terminates and R holds, then obviously this implication also holds. So first we look at the common rules for WP and WLP. So the just rewritten these rules that we have already seen for the weakest precondition, and basically these rules just carry forward to the WLP. So basically we can just replace the WP everywhere with WLP, and these rules work. So now we look at the abort rule. So what is abort? Aborts the program so control doesn't reach the PC after it. So by definition it is non-terminating. So what we have is that the weakest precondition of abort with the post condition R is false, while the weakest liberal precondition is true. This is because abort doesn't terminate. So basically for WP will have some precondition implies that abort terminates and R hold, but abort terminates it false. So we'll have the precondition implies false, so that has to be false. And so, but here if it says that if abort terminates, then R holds. So if abort doesn't terminate, so that implication is always true. So the weakest condition there is true. So as an example, we can see that the weakest precondition over this sequence of statements where x is first assigned y by z, then y is assigned x in time z is z not equal to 0, while the weakest liberal precondition is true. Note that we are assuming here that division by 0 causes abort. So now we're looking at partial correctness for a while loop. So basically we want to find the weakest liberal precondition of while e, the statement S, and then the post condition R. And basically in general both WP and WLP are undecidable. So WP is undecidable because of the halting problem, because it is saying that something terminates, and WLP because we want to find the weakest such condition, we have to find the loop invariant, which is undecidable as we have seen. So basically we need a loop invariant I such that I should hold in the beginning, and the whole triple I and E S I hold. So basically I hold across the statement, and on exit basically I and not E skip R holds. So I should hold in the beginning means it's hold at the initial state X, and for the remaining two statements they should be true for all possible states Y. So here's how we are encoding this rule. So the weakest liberal precondition is I. So basically this encodes that I should hold in the beginning, and then for all possible states Y, the second condition holds. So basically it says that so we are basically just taking this liberal weakest liberal precondition over S, and then we are just having this implication that I and E implies WLPSI, where X will be replaced by Y, because this all these statements I E everything is in the form of the initial machine state X, and we have to show that this is true for everything, so we'll replace X with Y. Similarly, we have that I and not E implies R, where R is the weakest liberal precondition over skip, and here also we'll replace X with Y. So we want to find the weakest such I. So to find the weakest liberal precondition. So as an example, we are looking at while x greater than 0, this is x minus minus with the with the post condition x equal to 0. So we are going to look at what are the candidate invariants. So first we'll have x equal to minus 1, and this is not a precondition because it does not satisfy this condition that for all y I and not e implies r, with x will be replaced by y. So so if we just replace I with x equal minus 1, e with x greater than 0, r is x equal 0, then we have this statement. And if we replace x with y, then we have this statement. And basically this is not provable because y is equal to minus 1 in this precondition and y equal to 0 in the post condition. If we take the candidate as x greater than 1, then it does not satisfy this condition that uh, this for all I y that I and e implies this weakest liberal precondition of s comma I. So basically this is the condition that it should be invariant. So if we just replace it, we'll get that initially it was x greater than 1 is our invariant, and e is x greater than 0. Then we have this weakest liberal precondition over a statement which is basically a x minus minus. I have just written it as x colon equals x minus 1, and this is the post condition was x greater than 1, which is I. So we just continue with this. So we'll first replace x with so we can first find this weakest liberal precondition. This we can do by using the assignment rule. So we'll replace x by x minus 1, which will get that x minus 1 is greater than 1. So and now we'll replace x with y's. And so basically this says that for all y is greater than 1 and y greater than 0 implies that y minus 1 is greater than 1. So basically it's saying that y greater than 1 implies that y is greater than 2, which is not provable. So finally we'll look at this candidate that x is greater than equal to 0, and it satisfies both for all y for both of the conditions that we had, and these are provable. Um, yeah. So it also we can also show that this it holds the exit condition, and we can show this by saying that y for all y that y greater than equal to 0 and y less than equal to 0 implies y equal to 0, which is true, and it's provable. Yep. Thank you.
Great. Thanks, Arpit, for that nice summary. That was very nice. So, yeah, let's open the floor for questions. Okay. Okay. Yes, Jay.
Hi, so I just wanted to know, so we discussed the partial correctness of a while loop, and it required us to have a loop invariant. So, how, since we also know that the total correctness is also an undecidable problem, so what, what limited techniques can we apply to at least argue about the total correctness of some examples?
Thanks for that question. So, indeed, I mean, basically, total correctness. So far, we have discussed how if we find a loop invariant, then we can basically show partial correctness. But loop invariants are not at all enough to show total correctness, because for total correctness, you also need to show that the loop will eventually exit. And this method of actually doing loop invariance will not basically tell you whether the loop actually exits eventually or not. So you need better techniques. And basically, at a very high level, the technique is to define some kind of progress function that shows that how the program state is going to evolve, and kind of have an abstraction for that. So for example, if you can say that, oh, I always, as the programming executes, I keeps decreasing. And then you say, because I keeps decreasing, eventually it has, and the termination condition is I equals 0. Then you basically use, the fact that if I keeps decreasing, it will eventually reach 0. And from that, you deduce that if the program keeps executing, it will eventually terminate. Right? So you basically identify what the termination condition of the program. Then you abstract what is the progress like some kind of abstraction of how we are going to progress. What is a kind of abstraction with which we can capture the progress of the program, such that this abstraction combined with the termination condition basically shows that eventually we're going to meet that termination condition. So that's basically the kind of things that go there. Yeah, so it's a different set of techniques, by the way, to do that, and we have not even touched those kind of techniques at all to basically do that. I mean, so I gave the example of I decrementing, but you can use another example like you're traversing a linked list or you're traversing a list or something like that. And once again, you need to have some kind of abstraction that okay, this linked list is actually a real list or something like that. And as you go along, you're increasing the iterator, and there's a limit to how big the iterator can be eventually. Maybe it's the size of the whole memory that you have anyway. And so eventually you're going to come out and so on. I'm assuming that the linked list is a well-formed linked list and so on. So, I mean, those are the kind of things that you have, I mean, that's the kind of reasoning that goes behind it. And this is more than just saying that, okay, what's the loop invariant here, right? So, yeah.
So it's like establishing like some order on the states and saying.
Exactly. It's about establishing an order, right?
Okay, thanks.
It's about establishing establishing an order, either a partial order or something like that, and then saying that I mean, it's like the semi-lattice has a bounded height or something like that, and then saying, okay, yeah, because it has a bounded height, then you're going to eventually terminate. In fact, this has a nice parallel with DFA, right? Data flow analysis. So when we talk about data flow analysis, what is a data flow analysis? It's also an execution. We start with some abstract set of values, we keep transferring them, and we keep executing them. And every time we kind of come to the same node, we kind of use a meet operator, right? So think of a data flow analysis as a program execution, except that it's executing on abstract states rather than concrete states. And our technique for reasoning about the fact that DFA will eventually terminate is that the set of states that the program can take can be infinite, but they are ordered through a partial order, and the height of that semi-lattice constructed by that partial order is finite. So in fact, the same technique that we use to reason about the termination of a DFA is basically, now when I talk about concrete states, there may not be a partial order at all, right? But or maybe the height of the semi-lattice may not be finite. I mean, you may not be able to prove that on concrete states, but if you are able to abstract them, then you will be able to basically say, yeah, now I can create an order, and now I can show that it is going to terminate. So conversely speaking, a concrete execution can be thought of as a DFA. Like an actual execution of a program can be thought of as a DFA, where the transfer function is just whatever executes. It's a forward DFA. The transfer function is whatever the machine does. That's operational semantics of the machine for every statement. And then the meet operator is just change the machine state based on what we have currently, right? But if you think of it as a DFA, the only issue here is that the set of values, I mean, there's no ordering between. I mean, I'm not able to say that the meet operator basically obeys the monotonicity, like the transfer function and the meet operator basically have the monotonicity property and so on. And so basically, that's the reason we cannot say that it's terminates. So yeah, there's a very good parallel between the two things.
Okay, thanks.
Okay, I have a question from Aditya. Aditya, would you like to turn on your mic and ask a question?
Am I audible?
Yes.
Yeah, so the whole logic rules don't seem to address memory, and so what will invariance related to memory look like? How do you reason with memory?
Okay, so the question is, what will invariance related to memory look like? In the whole logic rules that we specified, we only had a bunch of rules which were basically which we specified for our toy programming language. The toy programming language had a few constructs like skip, assignment, if then else, while, abort, etc. Right? Okay, so far so good, and we are okay with that. But a real programming language will probably have much more, and one of the important kind of things would be the notion of a memory. And what is a memory? A memory is basic. Think of a memory as a large array where you can use an address to index into the array and read or write that location. And so I mean, basically everything else remains the same. I mean, first of all, I want to point out that this toy programming language and the kind of memory, the programming language that we are talking about, they're both imperative syntaxes or imperative like syntaxes. And we're basically looking at those syntaxes because they are the common syntax kind of things that we use. I mean, if somebody else could have asked, oh, we haven't talked about functional programming language and what will happen in that case. And so, yeah, of course, I mean, we haven't covered all the possible syntaxes. We just taken a subset of the syntaxes and said, okay, how do we do it for that? And then we can generalize from there. Now, coming back to the question, like, how do we deal with memory, or how, if I was to generalize the whole logic for and support read and write to this array, which we also call memory, then how am I going to do that? So I guess one simple way to think about this is that memory is just another variable. It's an array, but it's just another variable. It's a variable of a different type. Okay, and so the only difference is that when you read something from memory, you basically, there's an operator called, let's say, select, which says, okay, select memory, comma, address. Just like you have a plus b, select is another operator. Just like plus is an operator on integers, select is an operator that takes a memory array as a first argument and an address as a second argument and returns a data value. So in that sense, select is no different from plus or minus or any other operator. And memory is just an array. If you write to a memory, you just created a new array, which is exactly same as the first array, original array, except that that particular location is different. So when you write to a memory, that's exactly like assignment. And when you read from memory, that's exactly like any operator, plus or minus or whatever. Right. I mean, that's a very high level view. Of course, I mean, these kind of things are, become very slow because I mean, typical imperative programs will have lots of writes to memory, right? And so that will create a lot of memory arrays. At a conceptual level, what I said is complete. I mean, is going to work, and it fits in our whole logic that we have discussed so far. But when we talk about actual implementations, we'll have to be more careful because we have to optimize and stuff like that. I mean, uh, uh, because memory arrays are. I mean, although memory arrays can be thought of as variables, I mean they're pretty big variables, and so we want to kind of be sure that we are doing the right thing. Uh, is there anything else here?
What about pointers?
What you are intending to basically get at is what about aliasing, right? So what if so basically what can happen is that the same address A, so I say select memory comma A, and I say select memory comma B, and it is not clear whether A and B could point to the same address or not, because I can kind of have two different variables A and B coming in. Maybe they have the same value, and then select A comma B and select M comma A and select M comma B should evaluate to the same thing. So that's what it boils down to. I mean, basically, in the presence of aliasing, I don't think what I said and changes in any way. The only thing that changes is that when you do, when you apply the whole logic rules, as you have, as I've emphasized over and over again, and as Arpit also summarized, it is basically the loop invariance that's the hardest part in this whole thing, right? Whether I look at it from the whole logic perspective or whether I look at it from the weakest precondition perspective. And in the presence of aliasing, these invariants become more complex. Okay, the required invariants become more complex because now you have to say, oh, I should be sure that A does not alias with B. In other words, A cannot be equal to B or something like that, right? And so it's just that the invariants become more complex, but other than that, everything remains pretty much the same. Does that answer your question, Aditya?
Yeah, I have one follow-up question to that. So, whole logic is complete for the toy programming language that was discussed, but is it complete for a general programming language? With
Uh, so the whole logic rules that we defined are for an imperative programming language. So if you say general programming language, going to include a lot of other stuff as well. But yeah, if I talk about imperative programming languages, which have these kind of things, I mean, you can add another operator or you can add another constructor or something like that. And like, for example, array dereference or something like that. And yes, I should be able to define rules for that as well. So in that sense, yes, I mean, it is complete for the kind of constructor that you use for in an imperative programming language. That's what this is meant for. Relatively complete, because we still need loop invariants.
why was the extension to separation logic done for whole logic? And that's actually what I'm trying to understand through these interpretations.
Right. So, I mean, you can basically build higher and higher level abstractions on top of whole logic. So whole logic gives you, by the way, whole logic itself is an abstraction. I mean, these triples, which we call whole triples, are an abstraction on top of first order logic because you can lower them down to first order logic anytime you like using predicate transform and stuff like that. So, so whole logic is an abstraction, and you may not be able to. I mean, in presence of loops and stuff, maybe it's not possible to lower it down. You need an oracle to tell you the loop invariant. But the point is that it's an abstraction. It basically allows you to specify things in a concise manner. It limits what you can specify. You can't specify arbitrary things, but you can specify things of interest. It's a higher level abstraction. Think of it like, I mean, maybe the first order logic is assembly programming, and now the whole logic is maybe like a higher level language, maybe like Java or something like that. I'm just using this metaphor just to say that it's a higher level of abstraction. And then you can build another higher level of abstraction, which is separation logic. Of course, we haven't discussed it in this course at all, but you basically want to say, oh, because this is a common scenario where there is aliasing and so on. One option is you kind of encode all these complex invariants in your as an invariant in first order logic. The other is you kind of build a higher level abstraction that captures that in the syntax itself, that these things are kind of disjoint or separate. And so, once you capture it in the syntax, then you define the appropriate rules. And once you define appropriate rules, then proofs become easier or more efficient. Because now you're dealing at a high level of abstraction. Not only are the proof obligations written in the higher level abstractions, the proof, the logic itself, has higher level rules. And so, you can kind of use the higher level rules to to be able to prove the obligation in a faster method way. So that's generally the approach, and even the whole logic is kind of like that.
That answers my question. Thanks.
Sure. Yeah, thanks for that question. I thought that brought good clarity. Okay. All right. So I want to talk a little bit about, we have been saying all along that invariants are should be given to us by the oracle or by the programmer or something like that, and without that, all bets we may not be able to proceed, and so it's an undecidable problem. Verification in general is an undecidable problem, and so that's now the question is that does that mean that automatic verification is a completely unsolvable problem? I mean, of course, it is undecidable, so that already means that it's unsolvable in general. But as engineers or as practitioners, we are interested in finding out that can automatic verification be applied to 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 kind of real world programs. Real world programs may not represent the extreme cases, that represent that kind of trigger all the undecidabilities and stuff like that. You should be still be able to, develop automatic algorithms that are able to identify what are the invariants for common kind of patterns. If you are able to generate a list of all kinds of programming patterns that people use. It may be a huge list, maybe million or billion, but if you're able to generate this list, then you can say, okay, now let's try to devise an algorithm that captures all these different patterns. Now, one approach is, of course, to look at each pattern separately, but that's not going to scale because, I mean, if there's like a million patterns, then that's not going to work. If you look at each one of them separately, it's going to take a huge, really long time for us to get there. But the first point is that, as such, in my opinion, this problem seems solvable. I mean, the way I described it, which is that if you look at all the programming patterns in the world and you say, okay, now let's try to write an automatic algorithm that's going to infer the invariance for all these patterns, then of course, I mean, if there's a finite number of patterns, eventually, maybe after 100 years, we should be able to come up with an algorithm that's able to tackle all those patterns after all. But you don't want to, and the question is, how do you do it? And of course, we are only, like, people have been working on this, and the number of papers that you have on just invariant inference is huge, because they basically, somebody writes a paper on this pattern and somebody writes a paper on that pattern, and each of those papers will basically say why that pattern is important from a real world sense, like why this pattern is very common, or why this pattern is very important, or something like that, or why this application for this pattern is very important, or something like that. And then they would basically say, okay, now that we have established that the application of this pattern is very important, or this pattern is very common, then they'll say, okay, here's the algorithm to basically do it. And the algorithm so there's a lot of work in invariant inference, huge amount of work, on invariant inference, and it's still very much ongoing. These invariant inference algorithms are typically very compute intensive, and they are typically modeled as search algorithms. So you don't know what the invariant should be, but you have some kind of a space that you define of possible invariants, once again based on all the kind of patterns that you assume believe that exist in the world. And then once you define that space, you try to search efficiently through that space. Typically, this space is huge, the space of possible invariants. And so the smartness of the algorithm is in traversing this space efficiently. Okay. I just want to mention, one very basic and very commonly used algorithm for invariant inference, which is called guess and check. It's not the most efficient way of searching the space. It basically relies on the fact that the space is already relatively small. And then what you do is, let's say you have a space of all the possible invariants that you think, you want to try out. Maybe none of them work, in which case you're not able to complete the proof. But if any one of them work, then the proof should be completed. So the search algorithm works like the following: that you just guess each one of them one by one. Okay. Or in fact, what you can do is you can basically say, let's assume that all of them hold together. And then you try to inductively prove whether all of them hold or not. Some of them will say, I'm not inductively provable. By inductively provable, I mean exactly the kind of proof obligations that we generate. They should be provable from the entry, they should be provable on the loop edge, I mean, they should be provable on all incoming edges. So in the case of the simple program where there's an entry and a loop and an exit, then it should be provable on the entry, they should be provable on the loop edge, and they should imply the post condition on the exit. And imply the post condition is kind of secondary, because if you are just interested in identifying some invariant, typically you are interested in identifying an invariant that satisfies the post condition. Just like we kind of, when we're talking about the weakest precondition, we were interested in identifying I that eventually proves R. Where if, as a WLP, if the loop exits, then R will be true. But so you typically people firstly split this problem into saying, let's not worry about R for now. Let's just say what's the strongest invariant I can find. So I have a set of candidate invariants, that's my space of invariants. And then let's try to find the strongest invariant that holds, that is formed by conjuncting or anding some subset of the invariants in this candidate invariance. So that's basically my space. So if I have, like, say 10 invariants, then the number of possible invariants that I can, so if my space is 10, then the number of possible invariants is 2 to the power 10, any subset of these. Okay, that's I'm basically describing the guess and check algorithm, by the way. I mean, so first of all, you define the space of invariants that you're interested in. You define it as n different possibilities. Let's say that n is 10. That space basically, that possibility space basically defines an invariant space of 2 to the power 10, because that's the number of subsets that are possible, and each subset is basically representing a conjunction of the possibilities. So there are two possibilities, A, B, then the subset A comma B, or let's say there were three possibilities, A, B, C, then the subset A comma B means A and B. So both A and B hold. Now, the first thing I want to point out here is that this space of invariants, there is an order. There's a partial order in the space of invariants. Some invariants are stronger than the other invariants. So I can basically, if my less than equal, if my partial order operator was basically how strong it is, let's say I draw an edge from stronger to weaker, then basically in this representation that would be correspond to the subset relation. A bigger set is stronger than the smaller set, right? Or superset, depending on which way you're looking at it. But so that's what it will be. And the algorithm is basically guess and check, which is you start with the strongest possible, which is the whole set, and then you see whether it is provable or not. If it is not provable, you identify which possibility it is that is not provable, and based on that, you keep weakening the candidate invariant. Each time the candidate invariant is formed by a subset of the possibilities. Anyway, I think, I mean, it's I think I'm just explaining by hand waving and stuff. This actually deserves at least 2-3 lecture modules of its own. But I just want to point out that there are these algorithms and people use them a lot to basically identify invariants. And this algorithm called guess and check is also called the Houdini algorithm, Houdini algorithm. Just in case you're interested, you're welcome to take a look. In fact, when we talk about data flow analysis, we are basically inferring invariants. Right. So even there we are inferring invariants basically because we are basically saying, we define some property. For example, the property is about constant propagations, whether X is a constant or not. So, that becomes, so we start with the strongest possible invariant. And then we keep weakening it until we reach a fixed point. Similarly, invariant inference is similar. You start with the algorithm, the guess and check algorithm that I described is similar. You start with the strongest possible invariant and you keep weakening it until you reach a fixed point. At the fixed point, all these invariants are inductively provable. By inductively provable, I mean, at all program points, if I look at all the incoming edges, then they basically, the whole triple, the corresponding whole triples will basically evaluate to true. So yeah, I guess, the long and short of this long discussion is that invariant inference is automable, can be made automatic till a certain extent. people are working on it in a big way, and there is a reasonable amount of success. And guess and check is one algorithm that is rather popular. There are other algorithms that are data driven, counterexample driven, and so on. I just want to mention these words, so just in case you're interested, you know what to look for. Okay. All right. So this is our last meeting, and I guess I don't see any. Let me just turn off the recording, and we can have some informal discussions.